Good morning. It is Tuesday, April 14th. It is a wonderful day to be doing calculus. The sun is shining, the grass is green, all that stuff. And we're going to be talking about change of variables for indefinite integrals and definite integrals specifically. It's important to note that we have basic rules in calculus which define our understanding of how to do a derivative and how to take an integral. The change of variable is a common technique that allows us to adjust how a function looks into a new specific form, such that when we integrate it, we can determine where the new function will be applied. Now, this technique is used numerous times in mathematics. We don't talk about it very much at the lowest levels because, quite frankly, at the lowest levels, it's not as useful. It's just easier to keep everything in terms of one function or one variable. But the farther you go in mathematics, the more important it is to have a fluid mindset when it comes to solving some problems. In other words, you can't always rely upon how a function is given to you. You have to be willing to manipulate it, to adjust it, to figure out the correct way to rewrite it so that you can solve the problem in its entirety. Now, for most of what we're going to talk about, we're going to be looking at something specifically called a U substitution. In this case, what we're going to be doing is we're going to be creating a function U that is going to be with respect to the variable we start the problem with. So the problem starts with x, we're going to change x into some function of u. If the problem starts with t, then we're going to change it with respect to u. Whatever variable we start with, we're going to change over to u. Why u? If I knew the answer to that question, I'd tell you. It's just a common form that people have used for a long time. You can do the same thing with the W substitution or a K substitution. It's just some letters are earmarked for a lot of different things. U hasn't been earmarked for very much, and so we use U pretty commonly in order to rewrite an integral into a better form. For most of my time today, I'm going to be focusing on examples because it is almost impossible to understand U substitution without seeing it in action. And so what I'm going to do is I'm actually going to do a few of your homework problems today. Ones that are not assigned, so you can see your assignment up here. Page 306/330, 39 through 85, every other odds, and then please add number 111. This will give us a good basis to go through and figure out all the different parts. And I'm going to use the odd ones to verify my results so we can see how this is done. Now, we talked last time about how to use substitution in order to rewrite using a reverse of the power and chain rules. It had us forcing us to use specifically, so from last time, it had to be in a very specific form. It's something of the effect of, you have to have f of g of x and then g prime of x has to be given in the problem, so that you could rewrite it using big F of g. This is essentially taking the chain rule and working it backwards, but it had to fit in this form. And the issue with doing it this way is that many functions don't fit the form, yet you can still find the solution by using this particular piece or this idea of creating a new function to substitute in for the old function. Let's take a look at some examples. In this case, let's go to your homework. I'm going to go to, it's not assigned, so let's look at number 31. 31 is a fantastic example that deals with how to solve an indefinite integral where you don't necessarily know all the components. So in 31, we have an integral of 1 over the square root of 2x. dx. Now, if this problem was the integral of 1 over the square root of x, we could solve it pretty simply, because we could rewrite the function into an integral of x to a negative power, and then solve using basic power rules. Here's the thing. That idea of like, oh, wouldn't it be so much nicer if we could do it this way? Well, as it turns out, we're actually going to do it that way. We're going to do that by forcing it to take on this other form. How do we do that? We declare the variable u. U in this case, I'm going to declare to be 2x. Why 2x, you might ask? Well, because 2x has a couple of unique things about it. One, I can find its derivative easily. That's a big detail when doing u substitution. When you do u substitution, you need to be able to find the derivative, or what we're going to call du. You want to be able to find it relatively easily. If you don't choose the right du, or if you don't choose the right u, it makes it very hard to find du, which is the next step we're going to take here in a moment. So picking u involves making sure that it's something that can easily find the derivative of. Next, when you take u, so when you plug in u, it needs to yield an easier form. Or you might prefer the phrase a more basic form. One of the ones from the beginning of the chapter, where it's a specific integral that we know is integratable, like this one. Like, we can't solve 31 with a basic integral, but we can solve this alternative to 31 with a basic integral. If we could somehow make it look like this, we could solve it. Now, I'm going to choose u equals 2x, and I want you to watch how this function changes. So we'd have the integral of 1 over the square root of u, but now we've changed the variable. We don't have dx anymore. We're now attempting to do this with du, which means it's an important note to take the time to figure out, okay, well, how do I get to the other variable? I can't just write du here. I cannot do that, because there is a relationship between x and u. So there is going to be a relationship between dx and du. So how do we determine what this is? I'll show you. We find du by taking a derivative. So we take u, we have to pick this. This is one we have to pick. However, once we've picked it, we can then find du by just taking a derivative of both sides. So the derivative of u would be du from our basic properties. The derivative of 2x would become 2dx. Now, if we can plug in for u into 2x, we can also plug in for dx. Dx we can treat like another variable, which means we can solve for it by dividing both sides by 2. And then everywhere there is a dx, we can replace it with its equivalent in terms of u. Because remember, we cannot integrate unless we have matching variables in the function and in the d component of the function. So, for this problem, the simple substitution creates this alternative equation. Where there used to be x, I have replaced with u. Where there used to be dx, I have replaced with its equivalent du, leading us to this newer, and you'll notice, easier function. We can take an integral of this function relatively simply because it matches this form we have and would be easier to do from the basic set list. So from here, I'm now going to follow my basic integration steps. All the pieces that have gone on so far are background pieces. They're not really a part of the problem, but they're necessary to simplifying the problem. They can be done mentally, if you're good, or they can be done in the underside of the problem in order to see all the components put through. So let's integrate this. I'm going to move the 1/2 out, and I'm going to rewrite as u to the negative 1/2 power du. I can now integrate. According to the rules of integration, when I have a power like this, I make sure they match. I would add 1 to the power. This would become u to the 1/2, and then divide by the new power. Now, when I divide by the new power, that indicates that we're going to have this new function, which is going to be divided by 1/2 plus c. So this is my new integral. Oops, we're not in a room. Okay. So I've taken my function, which started here. I saw, hey, I can't do this. This problem is impossible. It doesn't match any of our basic forms. So how do I do it? I substitute in u. But when I substitute in u, I can't just plug in u. I need to also plug in for dx. Because while I can get rid of x using the substitution for u, I get rid of dx using the derivative of u. Once I've plugged in all those components, I can then take a basic integral. And that integral leads me here. And I can actually simplify one more step. The 1/2 and the 1/2, because they're on top and on bottom, they can actually cancel. Leave me with just u to the 1/2 plus c. Okay? Now, this is not an acceptable answer. You need to make sure to take the last step is always to plug back in. We started the problem with x. We should finish the problem with x. So that's what I'm going to do. Everywhere there is a u, we know from before that everywhere there is a u, it is equivalent to 2x. So everywhere there is a u, it is equivalent to 2x. And this, as it turns out, is the solution to the original integral. Now, we cannot find this without rewriting it. It is impossible to get from here to the end without having this mediary u value. Because in order to integrate, we have only two basic options. We can integrate by taking a limit. The limit definition still applies, but those only really work with definite integrals. And remember, this is indefinite because there's no boundaries. And so this gives us an understanding of how to find those components. And we can do so by just taking the original function and transforming it into a basic function using a variable. This is the concept of u substitution, and it's a big one. It allows us to take some very specific steps so we can determine which exact pieces in question allow us to take these big steps forward. So, this is the idea of u substitution. It allows us to change the variable in the problem to a new variable without the necessary steps of being able to rewrite it. Now, u substitution is one method, and sometimes it is the best method. But that does not mean it's the only method, or that there isn't occasions where another method might work equally well. Let's look at the next one. For this problem, I'm now going to look at one like, let's do a trig one. Let's see, 47 should be in your homework. So let's do number 49. We're going to solve 49 by doing a specific substitution. Before we get to that, let's take a look at 49. Integral of sine of 4x dx. And afterwards, we will do afterwards we will do 54. Let's try that one, or something more fun. Okay, so here's the integral. Now, I can solve, if this was just sine of x, I could solve this easily. It's not. That's the problem. It's sine of 4x. And because it doesn't fit one of our basic forms, we're left with a question mark. Like, what the heck do we do? We can't solve this with a basic form, meaning it's not technically solvable, unless we are willing to look at this in terms of a u. Now, what you have to look at these problems and see is, what's the closest thing I could do to get this in a basic form? Remember, your basic forms are things like power rules, polynomials, fractional powers are fine because you can transform those into power rules. Or you can use a simple chain, like we did with the last time. And then finally, things like your trig functions, your basic trig functions that have their known opposites. So any one of these could be viable. You just got to be willing to take the time to figure out which one is which. So let's take a look and determine our answer. If we set u equal to 4x, that's step one. I have to decide, okay, what's my u going to be? I decided this u because it will get me down to just sine of u, which has an easy derivative. So I chose this because sine of u has an easy integral. So it's easy to integrate. I chose this specifically to get to this point where I know what my solution will be will get me something easy to work with. Makes it something malleable, something pliable. so you can find an easy way to get the solution. But if I have u, when I get back to the original problem, I can substitute in 4x for u. That's not too bad. So it becomes sine of u. But I can't just do u in for x. I have to also do for dx. So I take the time. I take the derivative of both sides. So u becomes du. 4x becomes 4dx. We don't do a standard derivative where we would have x disappearing because we want it to be in terms of dx. And so in this case, we can float the variable, allowing us to write u as du and x as dx. Okay, next. From here, we want to get dx by itself, so we can substitute back in for both components. So we divide both sides by 4. And perform our final substitution. Everywhere there used to be dx, we can replace with 1/4 du. So you can see how everything that started the problem is still in the problem, just written in a new form. 4x is still in the problem. It's just not written as u. dx is still in the problem. It's just written as 1/4 du. When you write one piece in a new variable, you have to write all the possible pieces in that new variable. From here, we integrate. So, sine of u, the integral of sine of u is negative cosine of u. The 1/4 would come out front, so this would become negative 1/4 cosine of u, and then plus c. For this part, I am using my basic integration rules. Remember, from a derivative standpoint, cosine becomes negative sine. So from an integral standpoint, sine becomes negative cosine. From here, I am not allowed to leave it in this form. I have to take the time to get it back to be in forms of x, but the nice thing is it just has u in it, so everywhere there is a u, we can replace it with 4x. So negative 1/4 cosine of 4x plus c. Now, you might be wondering, cool, we did some magic. How do I know if it worked? Because, like, if I don't have absolute faith in this answer, I may be questioning, did this actually get the right answer? And how do I know if it's right? Well, don't forget, you may always take the time in this particular type of problem to do a derivative. So I'm going to take the derivative with respect to x of this function. Now, because I'm taking a derivative, I don't need to do a u substitution. I just do a standard derivative. And if I take this derivative, it should match the original function, which is how I know what we've done worked. Because remember, integrals and derivatives are opposites. So if I integrate and get an answer, if I then take the derivative, I should get right back to the original answer. So let's take the derivative. Negative 1/4 is just negative 1/4. Since it's being multiplied to cosine, it doesn't do anything. We have cosine of 4x. That's going to be a chain rule. Cosine becomes negative sine. And then you have to multiply this by the derivative of the inside. It's a chain rule problem. Don't forget that. We have to chain the 4x inside. And the derivative of 4x is just 4. Now, when we simplify, negative and negative would make this positive. The 4 and the 1/4 would cancel, leave me back to sine x. And don't forget, c becomes 0. So it got us right back where we started. So we know what we did worked well. This is a u substitution, and we'll do a few more examples of these in a little bit, but let's make sure to understand where these pieces come from, and the big part, which is going to be, how do we get these pieces? So let's take a look back to this problem one more time. Look at what we started with. We started with this integral, which has parts that have a basic integral and a basic derivative, right? We can integrate sine, and we can also take a derivative of sine. We can integrate 4x, we can also take a derivative of 4x. So the question becomes, which piece do I want to make my u? Because in this problem, I could make 4x my u, I could make x my u, I could make sine of 4x my u. There are so many things I could do with this problem, because we are left to decide for ourselves what u is going to be. So when you decide, what you want to do is you want to make sure that the result is going to be easy to integrate. That's key. The result needs to be easy to integrate. Let's take a look for a second at number 56. This is an even problem, so it's not assigned, but I think it's worth taking a look at. Number 56, we have the integral, the square root of tangent of x times secant squared x dx. Now, when you look at this problem, you might be asking yourself, okay, well, I don't have anything like I did on 49, right? There's nothing inside of tangent, there's nothing inside of secant that I can do a simple substitution to. So what do? Where's my piece? Where's my u going to come from? So what you want to look for when deciding on your u, you want to look for derivatives that are either already in the problem or don't need to be in the problem, right? Up here, the derivative of 4x is a number. We can put a number anywhere we want using this simple substitution form down here. So that doesn't matter. If this had been 4x squared, we'd be in a different story, because the derivative of 4x squared would become 8x, and so 8x doesn't appear in the problem anywhere, and even a version of 8x doesn't appear in the problem. So you have to be careful making sure that it actually can be substituted in. But in this example, the u I'm going to choose is tangent of x. Why? Why on earth would I choose this? What makes this my best u? Two reasons. One, it's going to change the square root from the square root of tangent of x to the square root of u, which has an easy integral we can do. But that's actually a secondary consequence, because what it's also going to do is when I take the derivative du, the derivative of tangent is secant squared x dx, which you'll notice is this component. So I see that in my problem, not only is there something that I can choose to be u that'll make the integral easier, but its derivative is also in the problem. So when you're choosing your u, you want to make sure that you can find a du that's going to be easy or helpful. You want a du that's going to be either really easy to use or really helpful to use to make it something that's nicer in the problem. Okay? So going back to example, with u being tangent of x, I now change my integral. The integral, okay. Before I had to solve for dx because I wanted to do a substitution, but in this case, you'll notice that this entire thing is already in the problem. So I can actually do a simple substitution. Everywhere there is a secant squared x dx, it is equivalent to du, which means my function is now the square root of u du. What was I doing up here? I'm stupid. What is that? It's a mistake. Ignore it. All right. So look at how I changed my problem. Okay, again, this was the original problem. You can see right here in your text. It is number 56. My original problem is nasty. Like, there's no way to fix it. There's no function in my listing of integration properties that will ever fix this function. So it looks impossible. Or it looks like I'm forced to do an integral with a limit definition, which was not fun, as you might recall. Well, here are my alternatives. I use a specific substitution. This substitution changes this nastiness. And when I say nasty, it's nasty. The square root function with a trig function inside of it is nasty. I changed that from a trig function inside of square root to just a square root function. That's nicer, because that says an easy integral, right? You want to always choose one that makes it easy to integrate, okay? Not only that, but as a consequence, the derivative of the tangent gives me secant squared, which is the other component. So when you choose a u, you want to choose a u that's going to make an easy integration and has an easy derivative. So the tangent becomes secant squared, which is in the problem. Again, this changed how the function looked. It now looks like this. But let's showcase how we can get to our solution. So again, I rewrite integral of u to the 1/2 power du. And now I actually integrate. So we add 1 to the power, u to the 3/2, and then divide by the new power, which is 3/2, plus c. I'm going to simplify before I plug in for u. So this will become 2/3 u to the 3/2 power, plus c. And then everywhere there is a u, I'm going to instead put in its actual definition from over here. Everywhere there is a u, we actually put in tangent of x. So we have 2/3 tangent x to the 3/2 power plus c. Just like before, I'm going to verify this answer by looking at the derivative. Okay, so I take the derivative with respect to x of 2/3 times tangent of x to the 3/2 power plus c. I take the derivative. 2/3, not important, it moves out. The power of 3/2 has to be done first, so remember I multiply by the power and then subtract 1 from the power. And then multiply that by the derivative of the inside. The derivative of the inside is secant squared, because the derivative of tangent is secant squared. The 3/2 and 2/3 are going to cancel. This becomes tangent to the 1/2 power times secant squared of x, which is just a rewrite of the original problem. And so I know the original function worked. These are U substitutions. They allow us to take the function and manipulate and change how the function is written so we can have an easier time figuring out how it fits together. Now, we focused so far on indefinite integrals. How do I do the same process with a definite integral? Well, as it turns out, there are kind of two schools of thought on this, and I'll showcase both here. Let's take a look. Okay, for this problem, we're going to be looking at, let's see. Yes, let's do number 77. I like 77. If you're looking at numbers like 67, 69, 71, and 73, I will come back and do one of those here in a little bit. I just want to get this part out of the way first. Okay, so we have the integral. Sorry for that. We have the integral from 1 to 2 of 2x squared times the square root of x cubed plus 1 dx. So I look at it, my first thought is there any basic integrals? Like, always go there first. Don't try U substitution unless it's necessary. Always go for basics, okay? Especially with the trig ones, it's really common to look at them and say, oh, I must use U substitution. And it's like, no, you don't need to. It was a basic one. So make sure to look to see if it's basic first. Now with this one, it turns out I need to make some changes in order to get this to work because it doesn't match any of our current forms. So I need to choose a U. Now, I have some good candidates for U. I'm going to list them out actually. I could do just X. Because I can make U anything. So I could make U X, but that isn't very helpful, as we'll see in a moment. I could make U x cubed. This is helpful because if I make U x cubed, then the derivative of x cubed is x squared, so I know that's going to eventually cancel this thing out on the outside, so that looks pretty good. I have a third option of x cubed plus 1. Now, this last one is the best one, and I'll explain why. Not only does its derivative exist, right? The derivative of x cubed plus 1 is going to be 3x squared, and the 1's going to disappear, which x squared is in the problem. But when I integrate this, it has the advantage of taking this square root and making it into something that's relatively easy to use, because that's going to change this function from an integral involving a square root of a function to just the square root of u. It's the advantage of doing it this way. Now, if I'm going to use this as my particular u, this is my best choice, I need to now find du. Du is going to be 3x squared. Take the derivative of x cubed, that becomes 3x squared. The 1 is just a 1. Because I took the derivative of x, this would be dx. This part's really key. Make sure you keep the dx in there because that's the only way we're going to get it involved. Okay, next, once I've got this component, I can now try to do some rewrites. So let's take a look. I can't make this a 3 into a 2 without doing some fanciness. So I'm just going to move the 3 over and make this a 1/3 du equals x squared dx. And now I'm going to perform a substitution. The x squared and the dx I'm going to replace with 1/3 du. So the 2 is still a 2. And everywhere there used to be an x squared and a dx, it's a 1/3 du. You might ask how I can possibly move this x squared over with the dx when I have this square root in between them. Remember, these are all being multiplied. And according to the commutative property, I can rearrange multiplication into any order I want. So I could put the dx first. It just looks weird and is uncommon in mathematics. So we have our function rewritten using this new form. And note it checks off a bunch of boxes, right? The new form is integratable. When I move the 2 and the 1/3 outside, we get to a nice function, 2/3 integral square root of u du. This is a basic function. We can integrate this relatively easily by simply switching the form, 2/3 integral u to the 1/2 power du, and then integrating like before. 2/3 stays consistent, add 1 to the power, so that becomes 3/2, divide by the new power, which is dividing by 3/2, and then add c, because remember when I integrate I have to always have c, but keep in mind this entire function, before I go any farther, is definite, meaning that throughout this function my x value starts at 1 and my x value ends at 2. My x value starts at 1, my x value ends at 2. My x value starts at 1, and it ends at 2. And so for here, without that plus c, my x value starts at 1, my x value ends at 2. Now I can do a substitution. This becomes 4/9. Everywhere there's a u, I replace with x cubed plus 1 to the 3/2 power, and then plug in 1 and 2. Now this looks like stuff we did before. We can actually substitute this in, plugging in 2, plugging in 1, and getting to our solutions, which is what I'm going to do. So the 4/9 is just 4/9. I plug in 2. All right. 2 to the 8th power is, 2 to the 3rd power is 8, plus 1 is 9 to the 3/2 power, minus, plugging in 1. 1 cubed is 1, plus 1 is 2, so this becomes 2 to the 3/2 power, times that 4/9. 9 to the 3/2 is actually a nice number here. 9 to the 3/2 is 27, so 4 over 9, 27. 2 to the 3/2 power is not as nice. 2 to the 3/2 power is actually 2 square root 2. And so I can actually stop right here and say this is a good answer, because I really don't want to go any farther. It just seems not fun at all. Okay. This is one technique for finding an indefinite integral. Notice I switched my u to become in terms of x, using a very specific one, x cubed plus 1. I kept my boundaries in terms of x, though, because in the end, I make sure to switch back to x, and then I plug in the numbers like before. Becomes a basic substitution. There's actually a different way, which has a deviation right here. Now, 2 things to note. Anytime I introduce a new thing, I should always make sure to do this, and I'm terrible about it. Why is there another way? Well, 2 reasons. 1, it's faster. 2, it's easier. 3, if you get it. So, what we're going to do is when we rewrite, we chose to rewrite the function in terms of u. But I chose to rewrite this part of the function in terms of u, the actual functional part of it. But I can also rewrite one more thing in terms of u, the boundaries. If my u is equal to x cubed plus 1, then what happens if x equals 1? What happens if x equals 2? What that's going to do is it's going to give me new boundaries, but these new boundaries are going to be in terms of u. So when x equals 1, my u is equal to 1 cubed plus 1, or 2. When x equals 2, my u is equal to 2 cubed plus 1, which is 9. So what I can do is, instead of having to keep these x's involved the whole time and having to convert back to x's when I finish, take a look here. I'm going to take this part of my function right here. I'm going to bring it back down. We have 4/9 u to the 3/2 power. But now we're evaluating with it in terms of u. So from 2 to 9. This is allowable because we've changed all parts of the problem from x's into u's. It's like plugging in numbers for every x. We get an answer that doesn't have x in it anymore. Well, now we have a problem that doesn't have x in it anymore. It just has u values. Now notice the boundaries have changed. 1 becomes 2. 2 becomes 9. It became those values because if x is 1, u becomes something else. If x is 2, u becomes something else. So when we integrate, we have the possibility of writing it in this form. And when we actually plug in 9 to the 3/2 minus 2 to the 3/2, you might notice these two are the same. And that's because they have to be. You'll notice I avoid the process of having to plug it all back in and then having to plug in 1 and 2, basically doing 2 more extra substitutions. I can instead just do one substitution that does everything, which is why it's useful to have this u substitution, because you can change the entire problem in terms of u. Now, you cannot do this with indefinite integrals. The reason being is because indefinite integrals are going to have that plus c, and we don't know what c is necessarily. So we need to take the time to find that c if necessary. Or we leave it in terms of x because it's indefinite. But we can do this with definite, because in a definite integral, the variable is going to disappear anyways. The variable is eventually going to disappear no matter what we do, right? This doesn't have x in it anymore, so why would we bother converting back to having x in the problem if we don't need to? Now I'm going to do my next problem, and I'm going to do it all in u form. If I don't do it all in u form, you see how it takes a few extra steps to get back in terms of x, and then to plug everything back in and simplify. This time, I'm going to do it all in the u. Whew. Okay. Next problem. For this one, I want to do what one looks fun. I don't think... Ooh. Let's do 83. 83 has a fun little quirk to it, and I don't think it's assigned. Let me get a drink. All right, 83. The integral from 1 to 2 of x minus 1 times the square root of... Wait, I'm doing a lot of ones that have square roots in them. Let me see, can I skip one that has square roots in it? A lot of ones with square roots in this section. The reason why is because square roots are very common, and they're not nice to use. So Let me see. Is there a nastier one? Let's go to 81. I don't think if 81 or 83 is assigned. Maybe I'm doing a homework problem for you. Consider it a blessing. Integral from 1 to 9 of 1 over the square root of x times 1 plus square root of x squared dx. Okay, first thing, check. Is this a function that has a basic integral? Short answer, no, it's not a basic integral. Okay, part B. If it's not a basic integral, is there any way to rewrite this using a u substitution? And the answer is yes. Let's do it. So I can do this in one of two ways, and either way is going to get me there. It just kind of has to be done. Okay, ready? So I'm going to take my integral. I'm going to do the u. I'm going to choose 1 plus the square root of u. Or sorry, the square root of x. Why would I do this? Well, because I can see that the nastiest thing in my problem is this component. Like, this piece doesn't look nice, but it's being multiplied by something that's even nastier, and it's got a square inside of it. So I know already this is going to at least eliminate one big part of the problem. Now, when I do this, I need to make sure to get du as well. If I get du, it would be helpful to write this in a better form. This is 1 plus u to the 1/2 power. Okay, so let's go ahead and now do du. If I do du, then watch what happens. The derivative of 1 is 0, so that disappears. The derivative of u squared is 1/2 u to the negative 1/2 dx. Sorry, this should be an x. I'm stupid. Okay. Which, if I rewrite this, du is equal to 1/2 times 1 over the square root of x dx. And you'll notice this part is actually in my problem. These two components. We have dx being multiplied to 1 over the square root of x. So it turns out, if I move the 2 over by multiplication, so this will become 2 du equals 1 over the square root of x dx, I can rewrite this. Now, if you don't see that right away, you could take the time to rewrite this function like this. This becomes 1 over 1 plus the square root of x squared times 1 over the square root of x dx. These two are equivalent functions. I just rewrote them. And you can see much easier in this one that this component is right here. And so I can now perform my first substitution. Okay, so I have an integral. Okay, everywhere there used to be 1 plus the square root of x, I'm going to replace it with u. So 1 over u squared. So again, everywhere there used to be 1 plus the square root of x, I replaced it with u. So the square is still there. It's still on the bottom. Looks good. The 1 over square root of x dx, I now replace with 2 du. And now I need to make sure, since this is a definite integral, I need to plug in the boundaries. My lower limit and my upper limit. Let's plug those in. Now, how do I find those? I take my u, so I got to do when x is 1 and when x is 9. When x is 1, my u is equal to 1 plus the square root of 1. The 1 plus square root of 1, square root of 1 is 1. 1 plus 1 is 2. So this one has a lower bound of 2. When my x is 9, my u is equivalent to 1 plus the square root of 9. Square root of 9 is 3. 1 plus 3 is 4. Notice how this is so much nicer than the original. Like, no person that I have ever talked to would ever say that they would rather do this problem than this problem. But you have to see how they get there, and see how the components from the original get you to this function using this u. Now, from here, I can move the 2 out front. So 2 integral 2 to 4. I'm going to change u to a negative power, so u to the negative 2 du, and then perform my basic power rule integration. The 2 is still a 2. I add 1 to the power, so this becomes negative first power, then divide by the new power, which is negative 1. And then I'm evaluating at 2 and at 4. So my 2 is going to stay. My negative is going to move out. So this gets rid of those pieces. And then I have u to the negative first power, evaluated from 2 to 4. Okay. Let's do it. Plugging in 4. So I have negative 2 times 4 to the negative first power minus 2 to the negative first power. This one I will actually simplify all the way. So let's go ahead and take those steps. Negative 2. 4 to the negative first power is 1/4. Minus 2 to the negative first power is 1/2. Using power rules. 1/4 minus 1/2 should be negative 1/4. And negative 2 times negative 1/4 is positive 1/2. I showed a lot of extra steps in here, but notice I did not have to convert back into X form because I changed every part of the problem to be in U form. So the 1 and the 9 were replaced with 2 and 4, which came from plugging in 1 and 9 into X for U. So this allows me to solve this integral, and again, it puts it in a much nicer form. This is the new, this is the original. They both give me the same answer. If you grab out a graphing utility and plug this calculation in, it will pop out 1/2, or likely it'll pop out like 0.499999999, which is equivalent to 1/2 in all retrospects. So again, it can get us there eventually. The trick is, which is easier, which is done better, which is faster, which do you want to do more? So this is a version of indefinite integrals. Now, I believe that is the majority of our work. I have to get out of Bentonville. I'm donating blood today. I encourage you guys to stay safe, keep yourselves healthy, do what needs to be done. If you have any troubles, I know some people had some difficulties last week with getting their work in on my designated time. If you let me know, I am more than happy to work with anyone. I just want to make sure you guys get the grade you deserve for this class and get the information you need if you're taking the AP exam especially. So, everybody, make sure your homework is going to be due on Saturday, along with our assignment from Thursday. On Friday, I'm probably just going to have a day where we discuss some homework problems. And if you are having troubles with some homework problems, why don't you post that in the comments on the Google Classroom? And I will try to answer those specific questions in the next video on Friday. Okay? Not the Thursday video, but on the Friday video. So on Friday, I will try to have a question and answer time where I'll post a video where if you send me a question by noon on Friday, I will answer it in that video. So let's try to make sure that happens. If you need any assistance, let me know. I'll be happy to help out any way that I can. And let me know how I can help. I'll see you guys next time.